This all right. Great. So all the ideas that are happening get treated by the groups. And so for 6G, the first, time that we actually had a 3GPP meeting to look and start standardizing on 6G was back in March of 2025. And that's when, we came together and said, these are the technologies and work items that we want, work items and study items that we want to make it. And so then we've been kind of working towards that as part of this release 20. And in June 2025, after that initial workshop, there was an approval of all of the different study items. And in 2027, we're going to wrap up release 20 and move on to release 21, which will be the first normative release that'll have 6G specifications in it. And you can see, we're doing all this for 6G. That doesn't mean 5G stops. That doesn't even, there's still some actions, onto 4G and LTE that carry on a long way. And you can also see 5G Advanced has had things going on as well. So these are active standards. They take about 10 years to develop, but even after that initial 10-year period, there's still a long lead time that goes after them. And so just looking at things that are happening in kind of the 5G Advanced and this initial version of 6G and what's happening, I guess now we're in the second quarter of officially for 2026, but 3 of the 5G Advanced features that we're working on were NTN, so doing non-terrestrial networks and looking at GNSS resilient operations, so doing things around, if you don't have a GPS signal, what does that look like? ISAC, which is integrated sensing and communications, and looking at, I believe I have a slide in here. If not, I can pull one up, talking about the different, if you think about radar systems, there's monostatic, bistatic, and multistatic. And so they're looking at specifically the monostatic scenario. And then in AI/ML, they're looking at what's called dual-sided models, which is the idea that your handset is trained on a different set of data or a different model than the base station. And how does that work? For the AI and ML side of things, there's a lot of conversation around sharing data and data sets, and no one wants to share. That's essentially what it comes down to. The carriers have a lot of data from their networks, and that's proprietary, and honestly it's kind of equivalent to a trade secret at this point. They have access to all of that, and same thing on the handset sides. They have their own special things, and so Verizon doesn't want to share with AT&T, and American companies don't want to share with European, with Asian companies as well. So there's a lot of different corporate interests at stake there. And so in an ideal world, to get a handset and a base station to talk together with AI and ML, they would be trained on the same set of data, but realistically, that's probably not going to happen. So that would be the dual-sided model conversation. And then in release 20, the other big thing that's happening is looking at these study items for 6G and coming up with the recommendations for what's going to make it into the first version. So pretty exciting. We have a good idea, but we're going to get really firmed down and be able to say much more definitively what 6G will be in the coming months. And as I mentioned in the last slide, building out release 21 is going to be that first version where we're going to have 6G and be wrapping up in the 2029 timeframe and start rolling that out in 2030. So what are we doing in 6G? So that was kind of some of the 5G Advanced things that are happening. Between July of last year and July of this year, we're looking at the different deployment scenarios and regulations. There's also been a lot of work on talking about waveforms, if there's any changes that are going to happen there, on channel coding and modulation. A lot of that channel coding, modulation, frame structure, and energy efficiency, a lot of that's tied into how can AI and ML impact those, and then also looking at the test aspects of it. Important thing that just happened recently is kicking off and looking at what does next generation MIMO look like. A lot of conversations around NTN, both in terms of spectrum and in terms of how do we deal with things like Doppler delay. Spectrum aggregation, sharing, and duplex. So there's a lot going on in the standards, a lot of different things that we're studying. And in Malta, I believe it's next week, might be this week, they're kicking off a study group to look into integrated sensing and communications. All of that's going to get summarized at the plenary in June. So that'll be a big one, looking at the technology studies, seeing where they're at, do we need to make any adjustments, and then really doing some of that planning for release 21. Yeah, I can pause. That's a lot going on in standards. Any questions, comments, feedback, things that we want to dig into more? All right. So spectrum is kind of the next the next big thing. If you look at every generation of cellular communication, the one thing that's consistent between every single one is that they all had access to more bandwidth and more spectrum. So in 5G, we added in some lower bands around like 3.5 gigahertz. We dabbled in millimeter wave in like the 28 gigahertz space. But there's just not a lot of spectrum that's left that's not allocated, not being used for something. And so with the big thing now is figuring out where can we try and squeeze more bandwidth and squeeze more cellular comms in there. That's going to be either easy to reallocate the people who are already there or find ways that we can share. I think, there's a lot of spectrum around sub-terahertz, and that was kind of an initially pretty hot topic when it came to 6G, but it's really not been as commonly discussed in the last couple of years as it was at the beginning. So there's definitely still research going on there. There's still bands that are interesting. There's a ton of spectrum that's available, but one of the big learning from 5G, one of the key takeaways was millimeter wave's really hard. It's hard to propagate waves at those frequencies. Things like windows, instead of acting like a window, they act more like a mirror. So there was a lot of signal loss. We weren't getting the penetration from outside to inside that I think people were originally hoping for. The multipath environment is chaotic. So a lot of challenges from millimeter wave. So all the operators and even the handset folks are saying, well, can we use lower frequencies? And so they have a prioritized band that's called the upper mid band, which is between 7 and 24 gigahertz. And sometimes people will call it FR3 or frequency range 3. And there's a couple different bands that have been prioritized. And the one that really sticks out where I've seen the most activity and the most interest and most promise for becoming widely commercially deployed is the 7.125 to 8.4 gigahertz. And in the presentations I've seen from Nokia, they even go as far as to call that the golden band. So we'll see. And then there's US specifically has allocated some space for FCC study in the 12.7 gigahertz range. One of the big challenges with this frequency range, there's a lot of satellites there. And satellites are really hard to move because once they're in space, they're in space. So there's conversations around how do we share the spectrum. Telco doesn't have a good history of sharing, so we'll see if it happens. But then one of the other areas that we're seeing a lot of interest in right now for telco is non-terrestrial networks. And so I have some more slides later, but that's essentially what it sounds like is how do we use space and use satellites and take advantage of the reduction in cost that we're seeing to get a satellite into orbit and start moving some of their cellular comms to satellite based. And so you'll notice the terrestrial networks, they're really focused on kind of this sub 6 gigahertz and a little bit of this golden band. And then for the higher frequencies, they are looking at, how can we use NTN? So spectrum is another one where, again, a lot of things are happening. The ITU meets once every 4 years for the World Radio Conference, WRC, to look at bands and finalize them. It's for all of radio. It's not just for telco, but telco ends up taking the most of the time for it. So they met in 2023, and so the next meeting will be next November. They're month-long meetings. They're very intense, but so that's when we'll get some better kind of granularity and more finalization on the bands for 6G. But this is just kind of a picture of the latest that's happening. And with that, I'm going to jump into technology trends, unless you guys have any questions, comments. All right. So every company has their own version of pillars for 6G. And so this is the version that I helped create for what kind of what NI sees. And like 5G, 6G is not just one thing. There's a lot of different things. I'm going to start right to left. So either way. um, One of the big things that people are focused on is cost reduction. And we keep hearing this. How do we make our networks less to operate, less to deploy? People really got burned in 5G. They spent a lot of money to deploy new systems, new networks, and they didn't have a lot of new revenue streams coming in. So kind of the cost reduction pairs with this idea of new revenue streams. And if you go and watch any 6G conference, you'll hear a lot of people talking about like, oh, what are the new business cases? How can we change, the value proposition of telco? You have all of these technologies that have proliferated in the last 10 to 15 years that run on the backbone of cellular networks, right? So you have the Amazons, the Facebooks, the Googles that all depend on having a wireless network, but the carriers aren't seeing any of that revenue. So there's very much this reducing cost and new revenue streams aspect of 6G that are at the forefront of every conversation. So on the cost reduction side, it's looking at how can we do things to be more software defined. Instead of deploying new hardware constantly, it's, well, maybe we could just do it with a software update. And I have heard people say things as bold as, well, 6G is going to be the last G because everything else we're not going to need these large rollouts. We're not going to have to wait and go through this process. It can just be software updates. I think that's probably a bit of an exaggeration, but at the same time, I think there's some truth to that too. Another area that they're looking at is energy efficiency. I do some work in the sustainability and kind of the green space as well. And I was just pulling numbers. And if we look at the industrial electrical use for the United States, just Verizon, uses 1% of all of the electricity. And that's just kind of mind-boggling that like, to run our base stations for one carrier is using that much. And if you multiply that by 3, if you think about AT&T and T-Mobile, that's like 3% of our entire electric grid is just to power base stations. So there's a lot of room for improvement there. Electric's not free, so there's a whole lot of work going on that side. For new revenue streams, operators and carriers are looking at how can we make more money? What can we do that's different? What kind of services can we offer that are new? And non-terrestrial networks, NTN, and integrated sensing and communications, ISAC, are probably the two biggest ones that I've heard. And I'll touch on both of those in more detail, but I don't know how many of you are T-Mobile customers and follow this, but T-Mobile is actually partnered with some space, some different space companies, and they have early versions of this available now. Like if there's a package that you can pay for and get access to, text messaging via satellite. Now it's still, the data rates are really limited. It's still more or less tied to text, but it's something that's available, and it's kind of, your existing cell phone without any modifications can talk to a satellite today. And they do charge for that, but I've also seen they are kind of allowing emergency calls to go through for free. So they're looking at that as a new revenue stream. And the idea with sensing and communications is we have so many base stations out there, and if you can start to think of ways to use cellular signals like radar, you can start to get detailed information about the physical world around you through base stations, and so that becomes appealing. So you can sell off the data about the physical world. And then finally, the one kind of in the middle, just looking at improving our spectral efficiency. As I mentioned, there's just not a lot of free space. There's constantly more demands on the wireless network, and so people are looking at, what's the next evolution for MIMO and expanding into that 7 to 24 gigahertz. And then, it wouldn't be a presentation if you didn't talk about AI. I don't care what business you're in. AI is everywhere, and wireless is no exception. So AI is going to underpin all of these. So being everywhere, kind of just starting with the AI side of things, we see it being used a lot just in general. AI is great at optimizing complex systems. Um, Anytime, humans are great at doing simple things that an AI is not, but AI is good at taking, really complex models and finding patterns. And there are very few systems as complex as wireless communication systems. And so they are just like ripe for efficiency improvements with AI. So there's a lot of various different things that are being looked at. One area that's been being studied for, or I guess like three areas that were studied for a while, is like the channel state information. So the digital signal processing and computational load to look at the channel is pretty significant. So looking at, can AI help there? And then beam steering, beam forming is another one. Once we're talking about MIMO and you have, the large number of antennas for your phone or on the base station, being able to point a beam in a very precise location helps with that spectral efficiency. And but it's hard, and it's hard to do the initial like algorithms and searching to get the beam to lock is computationally intensive. And so that was another area where AI has been pretty helpful. And then I also mentioned the idea of looking at energy efficiency and reducing power consumption. We see AI being used there as well. So there's a ton of applications where we're already seeing AI being used, and it's going to be involved in all aspects of cellular. So we see it at like the physical layer. I mentioned the channel estimation, channel encoding, decoding. On the MAC side, so the timing, doing things like beam acquisition, and then at the network level, so even higher, doing data flow management. And then on the RF side, this gets a little bit into the sensing piece, doing things like RF sensing. But even if you're looking at designing a power amplifier, can you use AI to improve your impairments and doing digital pre-distortion? So I know some of our R&D team, we put out a paper just had a project. We said, okay, what can we do? How can we look at using machine learning for doing DPD? And so if you're interested in that, that's something you can find on NI's website and just read through what our team was able to do and some of their conclusions. And now I don't want to give you a sales pitch. That's not the point of today, but I am going to talk about some of the research that we've done because, like I said, we're pretty involved on doing wireless research. And so one of the things that we looked at for in cellular is this concept of a neural receiver. And so if you're going back here, I mentioned channel estimation, equalization, symbol detection, and channel decoding. You can actually, those are all three really computationally intensive processes, and you can combine all three of them and let a machine learning model do it. And so there's open source models out there that exist for this. And it's pretty common pretty common algorithm that people are trying to optimize. And so we're not trying to optimize the algorithm, but we came at it from a different angle and said, how do you test this? Like if people are actually trying to replace some of this traditional signal processing and put in a machine learning model, how do you know it's better? And you can use simulations and you can look at it and just say, okay, yes, my model in simulation does great. But what does it mean then to put that model inside of a real world system? Like, what does it look like when it's actually in a base station? And so we used open source software to get all of the software to run as the base station, and we used our software-defined radios as our front end. So we have our base station. We used, again, open source software to create a handset. We stuck a channel emulator in the middle, and then we ran through and we just tested out our model. We did a bunch of different training on it as well to train the model to make sure that like we could match the theory with theoretical numbers of performance for the model with training data. And what we saw, and kind of what's in this chart on the right hand side, is when we put that model into the 5G system, we had to trim down and make the model smaller so that it was able to run and meet timing. Now, if you do a Google search and it's using AI and it takes a half a second longer to get the results than if you were to use something else, use a traditional method, you're not going to know. But in a wireless network, you don't have that luxury. There's very, very tight timing constraints, especially on the physical layer and on the MAC layer. And so you have to be able to meet timing. And so you can't have this large, bulky model that takes an extensive amount of time to run. And so when we started trimming down our model to meet timing, we noticed that the performance gains that we were getting with our AI weren't nearly as good as simulation. Now, that said, you could still get some pretty good gains, but it forced us to have to go back and think about how we were training the model. And so the big thing that we realized is you can't get the big gains with AI and train for everything. Like, you really needed to be specific about what you were training for. And so, like, if we were to look at different MCS numbers, in this example, I believe this is the one where we trained looking at MCS 11, and you'll notice we have about a 3.5 dB difference. Whereas if we were, again, trained optimized for that MCS level, if we go up to 20, we're only getting about like 1.3 dB better. So there's some trade-offs to be used or to be learned for AI. And I think the other thing that we're seeing in this space too is as wireless engineers, we've spent the last 20 years trying to make all of our DSP highly optimal. And so there are a lot of pieces within a wireless network where it just does not make sense to use AI. The conventional methods that we have, some of the ASICs that we've developed, and some of the IP that we have is pretty dang close to theoretical numbers and hitting those theoretical maximums. So the real lesson is, like, use AI, but use it when it makes sense, and then learn how to optimize for kind of those best case scenarios. Other things that we did, so we took this same test bed and we said, okay, so great, we're learning. Now we're saying, again, we're an NI test and measurement. How do you now test a product that has a model inside of it that's running a machine learning model? Because, you know, and I think if you like read the news or watch what's going on with AI, you hear a lot about corner cases. And the one that always comes to mind for me is that, like, Tesla and their self-driving cars, and these corner cases where it's like they can't turn left in this certain scenario, or they're blinded by XYZ. And it's not all cases, but it's those corner cases that you want to know, and you want to know when it's going to fail. And so figuring out like what your test scope is and what your test plan is for things with a model in it is kind of a new it's a new chapter for looking at test and measurement. And so that's something that we've been working on. This is actually a project that we did jointly with UT and some of the folks there. And they have some great papers on this as well that I think were at PIMRIC last year. But what they were working on with us is looking at not failing when we think it's going to fail, but when did it fail when we thought it was going to pass? So looking for unexpected behaviors, unexpected failures, and unexpected passes, and trying to get better at determining when those are so that we can minimize the amount of testing that would need to be done on things that contain ML inside of them. Yeah, and so, like I said, we worked with UT Austin, Professor Kaushik Chowdhury, and there's the paper if anyone is interested in learning and doing a lot more detail and deep dive on the work that we did there. But really cool stuff, just really kind of interesting, and maybe not things that you think about every day when you're looking at AI and how it's going to impact your work. But again, like I said, we're not here to be advancing kind of the wireless algorithm side of the world. We're thinking about this with maybe a slightly different lens. All right, so I mentioned the greenhouse gas emissions and looking and seeing that, like, Verizon is using 1% of our electric. The other thing to note is, you know, if we were looking at the overall carbon emissions, again, ICT, information communication technology, that's where all the wireless falls. We're using about as much, we have about the same carbon footprint as the aviation industry. And by some estimates, we're close to double that. So cellular is huge. We're huge polluters, and there's a big desire to clean that up. And the kind of the obvious place to do that is through the base stations. So I think, you know, there's looking at where within the base stations things are being used. So power amplifiers is a big one, core networks, just even air conditioning to cool the base stations to keep those power amplifiers happy. Um, so obviously, how do you turn off these things? How do you generate less heat when you don't need it? And that kind of also ties into this idea that 20% of the sites carry 80% of the traffic. And so how do you optimize, right? And so as I mentioned, AI is really good at optimizing these complex networks. Because we could just start turning amplifiers on and off, but people still want their phones to work. So it's a balancing act of how do you find the right quality of service metrics and tie that to the right energy efficiency. And so we took our kind of neural receiver system. So we had the same thing where we had, um, the machine learning model on the base station, talking to our software-defined radio handset. We stuck a power amp in line with the radio for the base station to kind of give a little bit better understanding of what a base station looks like. And then we added on some power measurements. So we're looking at voltage and current at multiple different parts throughout the system. And then what has been, kind of one of the big challenges is correlating that data. So how do you have a power measurement that correlates to what's going on at a packet level for your wireless network? Because it's not good enough just to know how much energy you're consuming or how much energy you're saving. You need to have kind of that deeper level of understanding to know what, cause and effect, right? If you change something, can't remember if I put the slide in here or not. Yeah. So if you're looking, if you were to change the power per slot at the MAC layer and change the different configurations, what does that do? And having a way to look at that kind of power consumption over time in your power profile and mapping it back to what's happening in your downlink slots, your uplink slots, and like having a slot to slot measurement is really important to being able to make these kinds of improvements to the physical layer, improvements to the MAC layer, and at the end of the day, save some electricity, save some carbon within this space. So this is another area where we've been really active in trying to do some joint research. We work with Barkhausen Institute, TU Dresden, and then we're also working with Yonsei University out of Korea on this. So a lot of really cool research that's been going on there. Just also a really passionate community of people who are interested in sustainability, trying to make our networks green. All right, I'm gonna pause. So that's the end of my AI section. Any questions, comments? All right, I think we're doing all right for time as well. So integrated sensing and communications, ISAC, sometimes also called JCAS, is one of the next areas that we're seeing as very popular for 6G. And that comes from being able to add sense to the network. And it's unlocking a bunch of new applications that operators, carriers think that they can monetize. So, doing network twinning, looking at traffic control, having an understanding, like you said, of the physical presence around you. So you can even do location tracking. Some of the other areas where I've seen this talked about is doing like gesture control. So if you look at kind of some of the wireless headsets and things that are coming out, it's how do you, instead of having a sensor on your wrist, can you do it all with gestures and have the wireless signal and the way that it changes actually responsible for that. So a lot of cool things going on there, a lot of different research that's happening in those applications, but pretty clear that this is going to make it into 6G and be one of the defining features. Yeah, here's a little bit more information. I'm not going to read through all of these, but just give you an idea of stuff that's happening. This idea of robots inside of a factory is really important, right? So how do you get centimeter level of accuracy? And it's not just to be able to automate factories and do robot control, but it's looking at how do robots and humans interact, right? Because if you are a person that's on the floor and your robot's moving, having that level of accuracy and understanding how, if a robot arm is swinging at you and you're walking, you want that to stop instead of causing an injury. So there's some cool stuff going on in the industrial space. Yeah, there's just there's a whole lot. We could spend a whole hour talking about ISAC and what people are trying to do with it. Um, but as far as, what does this mean like practically and what's some of the implementation, there's a lot of really like great hand wavy kind of ideas of where we can get. I think people want to be at this idea of signal sharing where everything is the same, but like realistically, it's hard to get there. And so the first thing we're looking at is like, okay, can we have our base station with our regular communication signal that's talking to our phones and then have some sort of traditional radar that would be installed on the tower? Next level of integration would be, okay, so again, they're probably co-located and now they're sharing spectrum. So comms signal goes for a little while, break in time, and then the radar signal, and then comms, and then radar. Next level of integration is saying, okay, well, so maybe it's just the cell tower. You don't have a second radio that you need anymore. And so now you can either blend it in time or blend it in frequency, but it's that same piece of hardware. And then kind of like the gold standard, that'd be great, is actually sharing the same signal. And there's reason to believe that we'll never truly get all the way to the signal sharing. Yeah, we'll likely get to the same waveform, but to have the same signal sharing, like you need to more or less be transmitting constantly from the base station. And for the environmental reasons that we just discussed, people don't want to do that. You want to be able to turn things on and off. But what we're seeing is, there was a lot of conversations early on of like, do we need to modify the waveform? Do we need to do something different? Do we need to allocate a certain amount of bandwidth for like an FMCW signal? And what's really kind of the latest I've heard in like the conversations that where we seem to be is like, nah, OFDM is good. And if you look at an OFDM signal and kind of like break it out and look at it in a grid, there's different parts of an OFDM signal that vary in time and different parts that vary in frequency. And so, you can use your reference signals that would act like a pulse train in time. And so you can use those to do sensing and look at, kind of the velocity. And then you could use your range can be estimated within the OFDM symbols and looking at the subcarriers. So just natively, the way that OFDM is built, it's actually a really great radar signal. But there's trade-offs. And so you have to think about, what what are you designing your signal for? What are you designing your hardware for is the other thing. And optimizing there. And like if you look doing higher order QAM, higher order modulation, which would get more data throughput, is going to have worse performance for the radar side. And the other thing too to consider is once you start kind of making some of these tweaks in your system, you also need to make considerations for your hardware too. If you if you look at the cost difference of like high-end radar versus the cell phone, they're different, and they're different for a reason. And part of that is because the receivers on the radar systems are so sensitive, and so they have really, really good RF front ends. They're very clean, whereas on cell phones we don't. Like the way that the standard's been designed, all of the coding and repeatability. If you miss a symbol, it's fine. And so there's some actual like truly different design practices between the two applications that if you want to make a sensing system, there's going to need to be some kind of merging and just consciousness of one versus the other. And for some of this stuff, AI can play here and be helpful. And for some of it, it's going to be changes in our design practices if we truly want to implement this. All right, I'm going to try and share a video. We'll see if it works. But this is a demo that one of our partners did. So they're using this open source software, OAI, which built up a 5G base station. They have a radio on the front end, and then they're using that radio kind of with just this existing waveform. They didn't do anything special. And then using AI, a combination of AI and algorithms to look at room surveillance. And this isn't necessarily new. People have been using like Wi-Fi signals for fall detection for years. It's pretty cool. You can actually like look and just see, where is someone in a room walking around based off of the way the Wi-Fi signals reflect off of them. So this concept isn't entirely new, but it's pretty neat. So I'm gonna see if this will work. I haven't tested this on Zoom, so let me know if it doesn't. and I'll mute that because there's actually no audio that goes with it. But you can see, so they have a handset on one side of the wall, the base station with the software-defined radios on the other, and they have, someone walking around through the room. And if you were to look at the signal that's being received, you can see kind of these, what they call them is like deep fading. So you can see areas where the signal passes in front of that handset, the power level goes down, and so you can, map out what your empty room would look like, and then use that in some machine learning, train it, and then be able to build a map out of where a person's walking. So, like I said, this isn't like entirely cutting edge. I found a really old case study on just even on the NI website of someone doing this back in 2012. So this has been around for a while, but we're starting to see more of this and capitalizing on the idea that we have an incredibly wide range of sensors already out there just using wireless and looking at creative ways to use signal processing to do to add sense. Oh boy. I don't know how to go to the next slide now. So give me a second. Challenge with embedding videos. Nope. Okay. Can you still see my screen? Or do I need to reshare?
Yep. Yep.
Okay.
I can see your screen.
All right. So, I guess again, pause. Any comments, discussion? Keep on blowing through. If not, so one of the other areas where again we see an opportunity for new revenue streams is this idea of using non-terrestrial networks. Looking at things, I think at this point a lot of us are familiar with the idea of doing broadband internet. SpaceX is one of the big ones with I'm forgetting now. And then Amazon's launched Kuiper, and there's some other companies that are looking at doing that too. So that's, I think we've heard of that side. I mentioned the idea of doing narrowband data. So currently we're looking at like SOS messages for handsets and kind of emergency, and then looking at doing just whole networks and trying to get to a point where we can do phone calls and voice. It's really hard. We're still, the data rates are still very, very slow. Text messages even can be a little bit slow, but that's one of the goals that we have. And all of this really is made possible because of the decrease in cost of launching satellites. This is not the first go around for NTN. There were actually companies that tried to do this back in the 3G days, even kind of as early as that, but it was just so expensive. The business case never worked out because people would get it, they'd step outside, and yes, they would have signal, but it was really slow. And even for 3G, it was considered very slow. People were starting to want to get data and do things faster and do more than just send a text. I think they've done a little bit better job of messaging the capabilities of this right now. I think the broadband providers are proving that it's possible to get these high data rates, but as soon as you start adding in the idea of mobility, then that's one of the big challenges. So there's a goal to get all of this going and to have true global cellular coverage. And there's a bunch of different ways that folks are looking at it, kind of ways that you can have the satellite and kind of which pieces they're doing and where they're acting as the gateway, and how the service is going. Like, are you going to have an actual base station that's up there on the satellite that's beaming things down, or are you going to have a base station on the ground that then just kind of like uses the tower or the satellite as a receiver? There's still a lot of configurations that could work, but looking at kind of these different links and understanding what's going on with the channel is still, there's still a lot of work. There's just a lot of work left to do there. So it's a really exciting area. I think we're already starting to see kind of some of the initial results. There's a desire to push some of this through on the standards, but we're also seeing people that just say, does this need to be standardized? There's certainly a desire to have it work with commercial phones. Nobody wants to have a special phone to interact with this. But at the same time, I think all of the different suppliers currently are looking at slightly different implementations, different IP, different waveforms that they can use to make that happen. So still a little bit of Wild West out there. There is more aspects that are happening in 3GPP right now. I think one of the big reasons that people like the idea of going through standardization is to get access to spectrum. I think 3GPP carries some weight and can help make some influences there, but we'll see what happens. So yeah, keep an eye on NTN. All right, the last topic I have is around the idea of the softwareization of networks. And so just to give a quick recap, there's we've been working towards open radio access networks for a long time. And so we started off, back in the day where, nothing was virtualized. And then we moved to CRAN, which is a centralized RAN, where, we had the baseband unit, BBU, and then there was some backhaul to the core. And then we've been slowly moving towards, we have more virtual RAN. So some of the packet cores running in the cloud, some of the BBUs running in the cloud. So there's pieces that have been virtualized. And then what we saw start to happen kind of in the same time frame as 5G, not a part of the standard of 3GPP, but really like influencing it was this idea of open RAN. So disaggregated and open, where you have it's no longer just a virtual baseband. You now have a virtual CU compute unit, DU distributed unit, and then adding on things like the RIC, which is I'm gonna get the acronym wrong, but it's like a control that goes in between them, and then we still have the virtualized packet core. And the thing that ORAN wanted to do in particular is to have open front haul and open interfaces between all of these. If you look back at kind of the centralized RAN, virtualized RAN, they were using CPRI, which, everyone said, oh, CPRI is going to be great. It's going to be something that we can all standardize on, then we can have vendor interoperability. Didn't happen. If you get CPRI from one company, you're kind of locked in. And so the idea with Open RAN was to white box everything so that you could have a bunch of different vendors to make up a base station. You could have a vendor that did your ORU, so the open radio unit, and then connect to a different DU vendor, a different CU vendor, and kind of put all of this together. But knowing since there was the open interfaces and common interface between them, everything would just work. Great dream. Hasn't entirely happened, but people are still working on it. And so one of the things that happened with ORAN in particular was the idea of what runs on the radio unit versus what's running in the CU and the DU. And so, pre-ORAN, pre-5G, there was, it's called split 7. And you can look, there's a bunch of different ways to split the processing. So on your radio unit, you have your RF, so your up and down converters, your mixers, your filters, your amplifiers, digital analog converters. And with the traditional split, that's it. Like the radio unit truly is an analog thing. And then it sends you back your time domain samples, and then the CUD do all of the digital signal processing, including the low physical layer L2, L3. The 7.2 split takes that low phi and moves it onto the radio. And so now you're doing some of the signal processing, and instead of sending time domain IQ samples, you're sending frequency domain IQ samples. So you're running the FFT on the RU. And that's kind of one of the big differences that we've seen, but it was the idea here to make it easier again for some of those interfaces. And, is it going to be a game changer? Well, it depends on who you ask, but I do believe that, the ORAN is kind of the future. And if we look at anything for 6G, it's really based around more of this softwareization, more of this interoperability, and having open interfaces. And so, for the ORAN front haul, you can do your FFT on kind of this nice hardware at the RU, which is not necessarily ideal for the host PC. You can standardize on the interfaces, and then you can typically make something cheaper. And it'll be cheaper than a fully flexible SDR. So it's great for a lot of reasons if you don't want to touch the PHY. But if you're someone who is interested in actually doing research on the physical layer or on the RF, it can be a challenge. So it locks you into OFDM. There's no looking at new frequency ranges like FR3. So there's a lot of kind of like pros and cons of why this would be interesting, but we're seeing a lot happen. And so one of the things that we're one of like the latest big things and drivers of this is called Okudu, and it's Open CUDU. And this is an initiative being driven by the United States government, and they're calling it the Kubernetes for the RAN. And so Kubernetes was a common layer for a cloud infrastructure. And, there's an idea that we want to shift from how do you run and build containers to what services do you build. And this is in line with a lot of what operators are telling us, right? Like they want to build APIs for the networks. They want people to think about building services on top of what they're offering, not running and building containers. Um, and they want it to be the big thing, the big push here that we're seeing is they don't want black boxes or white boxes with interoperability. The US government is pushing for an open source software stack and an open source implementation. And this gives the DoD complete visibility into the stack and into the supply chain for doing security. It would be open. We can use AI to optimize things. And it would help break away from that 10-year innovation cycle that we're seeing with 3GPP. So it's it in some ways it's extremely radical, but in other ways it's just following the technology trends that we've already seen. Making it open, though, I think is is ruffling some feathers, and there's some people that are very in favor of it and some that aren't. And I was hoping our friend from Ericsson would be on. I know he said he had conflict tonight, but I'm very curious to pick his brain on what Ericsson's thinking there. But this is actually just a slide that I took from someone at the Department of Defense. They're running a program called Future G. There's like I said, the U.S. government is putting a ton of money behind this. Like they have entire projects for this. It's multi-million dollars of investment wanting to make this happen. And so if you go and look at kind of the Future G motivations and missions and Future G comments around Okudu, you're gonna find a ton of stuff that's happening. And there's kind of three different pieces of looking at the hardware, looking at the management, but a big one's on the software and creating that open source stack and making. I don't know how many people use open source software and are familiar with these tools, but OAI is great, but I would not call it carrier grade. It's very much an open source project, and it's a little bit rough and ready. It takes some time to get it running, but it's great, especially considering it's free. And they have a lot of features there, but it's lacking to get to that carrier grade. And so that's one of the things that they're looking for, building out and then having kind of this open ecosystem. So like I said, pretty big shift, but also a lot of force being put behind this. So, we know today that there's partly open sourced implementations, but they're looking to build out kind of in the next, I want to say the next 2 to 3 years, have this security, transparency, and speed for building out our new version of the RAN. Yeah. So I have more information here that we could talk through if anyone has any particular questions. But with that, I think we're at kind of a good point on time. Go ahead and wrap up and see if people have things they want to discuss.
Hi, question.
Yeah.
On the low Earth orbit satellites, do I
Yes.
understand that they last only about 5 years? And
Yep.
doesn't that worry people that if there's any interruption in putting um, things back up into space, that we could lose the network entirely in 5 years?
It worries folks like me. I think it depends on who you talk to, right? There, I come at it too from thinking about isn't that going to be ungodly expensive? Isn't that going to be really resource intensive? Yeah, I think that's kind of one of the questions that anytime I'm in a panel, I ask because I am curious and I haven't heard a satisfactory answer. So it is something I feel like that gets glossed over at this point.
I have a question. Can you, um, there's all of this desire to capture and monetize communications from the edge.
Hmm.
And all of the examples that I've seen, people, you don't, do you really want to connect your washing machine to the wireless network? I would guess maybe Whirlpool wants to collect some knowledge, but it doesn't do anything for me, and I'm not willing to pay for that. Do you have any insights on why there's this continuing goal to
Yep.
what are they going to do on the edge?
Well, I think as a question of like that blurs the line too between cellular and Wi-Fi. Like folks like Whirlpool wanting to connect your uh, appliances to the internet, that is all about data harvesting, right? That's getting data on consumers, doing it over the Wi-Fi, and selling your data and your privacy goes out the window. So that is a very like specific use case. For the cellular side, I think there's this idea that goes back again to ISAC of building out this really robust network of sensors, and it feeds into multiple different applications of things. There's things that could be kind of nefarious, like location tracking of everyone and having this idea of what's going on. But if you think about it, they kind of already know you have your phone in your pocket. But so it's looking though at making that more complete digital picture of the world around us. And then once you get all of these sensors out in all of these different locations, you can start to build digital twins and do a lot more with kind of on the simulation side and like the emulation side to build out more complex models and do more twinning, and building out things in a more robust way in a virtual world without having to build them in a physical world first. And that's kind of one of the key applications that I would see. There's certainly others that go there as well. But yeah, think about it as like low cost sensors.
Okay, thank you.
Yep. All right. Anyone else in the group?
And maybe it's too basic. So with the 6G coming in, will there be any effect on like more radiation from the devices or the device battery life? Will it also define? Because what I understood, right, and G level, right, ability to 5G, high time that you use battery is supposed to drain faster. So
Yeah.
how is it going to affect in terms of device health or in terms of radiation? Do you have insights on that?
So there are different research paths of looking at kind of how to improve the battery. Smart sensors, like if you were to put a water meter or something else that would have to be battery powered, there is a lot of concern, right? Like, and this goes to Dennis' comment about like building out things on the edge and building out what we've called for years the Internet of Things, and like truly doing this and having connected everything that's not always connected to a power source. Um, I believe it was called 5G Lite for a while. I think Red might have been Red Cap is what it ended up being called, reduced capability. And there was a lot of work around like the idea of wake up signals. So how often is your phone or is the device like checking for that signal? How often is it sending a signal back? How often is it kind of like in deep sleep? And so yes, there are ongoing efforts of that, and there was a big push in 5G, and there's still some continuation into 6G, and then just the idea around using as limited resources as possible for everything, to make 6G more energy efficient is simultaneously happening. Um, I wouldn't say there's like a ton that I've seen around going up to super high frequencies or increasing the power. Um, but it's more been around reducing power, honestly, to make batteries last longer, to make everything last longer.
Okay. Another follow-up question, if that's okay. Yeah.
Yeah, of course.
So one other question is about the signal amplification. So usually when we have all these towers on the ground, we use them as an amplifier, right? To boost the signal, and then the nearby cell phone signal will be strong enough. But when we are depending on the satellite, so how this signal amplification will be taken care of?
Yeah, I mean, I don't think so. You have different challenges, right, for signal amplification. If you have a, a tower in your from a satellite versus a tower on the base station, and so like where I am, I actually I don't live in Austin anymore, but so I'm in a very mountainous area, and I actually don't get cell signal from my house, and it's not necessarily because there aren't cell towers close to me. It's that there's a lot of mountains, and it goes like this, and so getting enough power to get a cell tower or cell signal through all of those mountains is just not ever going to be realistic, given the propagation challenges of that. But if you have a satellite and you're just beaming down in one direction, it's actually in some ways easier because you don't have large amounts of rocks. And if you're looking at someone that's on the street too, you don't have to worry about like, do I need to go through buildings to get to that person? You're just beaming down. And so the channel itself was actually quite different. And so there's a new set of challenges with that. But I wouldn't say that like amplification is the number one problem, because they can put like really massive amplifiers up in space, and be able to send like large amounts of power that get attenuated to something that's quite reasonable by the time it gets to us. You got to worry about rain and other things like that. But yeah, it's just a different set of propagation challenges.
Thank you.
Yeah.
So if anyone else has a question, please feel free to ask.
Well, if not, yeah, thanks so much for having me. I know we do this, you guys have asked me to do this about, I don't know, once every 12 to 18 months. I'm always happy to come talk with the IEEE folks. So
Thank you very much for your time.
yeah,
And it's a very interesting topic.
yeah.
Do you have any contact information where if somebody has a follow-up questions, they can reach out to?
Yeah, it's my first name dot last name at emerson.com. And let me see if I'll just drop that in the chat for everyone.
Sure.
And Uday, I don't know if it's you or Kai, but I'll make a PDF of the slides and I'll send those to you as well so that everyone can have a copy.
Sure.
Okay, great. I was just gonna ask that. Thank you.
Yeah, no problem. So I'll get that out to you guys either later tonight or tomorrow.
Okay. Thank you.
All right. Well, thanks again for the invite, and looking forward to doing it again in another 12 to 18 months.
Thanks.
Thank you very much.
All right. Thanks, everyone. Have a good night.
You too.
Bye.